First of all, I will thank the organizing committee for her invitation, and it's a great pleasure for me to meet the colleagues and everybody which are present here. It's also a pleasure for me to be in the beautiful city of Vijaya. First of all, I will present our school. Our school is situated in the west of France, in the area which is called Brittany, Bretagne in French. This area is known as the earth of the legends, like Merlin the Enchanters and the Knights of the Round Tables in French, Merlin l'Enchanteur et les Chevaliers de la table ronde. I came from the school of National School of of Chemistry, Engineering School of Chemistry. We have 4 great labs working on different themes, like materials, like environment, heat, and catalysis. So we work on environments. Our activities, research activities, can be summarized by one term, that oxidation process. Our objective is to develop oxidation process to reduce the pollution. This oxidation process can be non-thermal plasma, can be photocatalysis, or the combining of them. Adsorption is not an oxidation process, but it can improve the efficiency of the degradation. The effluents we are studying are concerns air, indoor and external air, for example, and water also, wastewater and potable water. Here in this slide, I will represent our usual approach when we have a problem to study. First of all, we go from an initial idea. It means that we have a problem of pollution, for example, air effluents of farms. So we study at a scale lab the possibility of the degradation of the pollutants by photocatalysis, by plasma, for example. Then we increase step by step the study by increasing the flow of the effluent will be treated. Then we go. The last step is to test the prototype on the site, on a real site where we have an effluent containing the pollutants and other pollutants like solid particles, for example. Simultaneously, we study the theory of the oxidation. We simulate the phenomena by using the tools we have on our disposition on chemical engineering. I will present this after. And also we do chemistry by determining the chemical pathways of the degradation, and essentially we need to know the formation of byproducts, because we need to control them. The idea is not to degrade the first molecule and create a molecule which can be more toxic than the initial molecule. Our research activity can be summarized by 4 challenges, and I can see this. The first challenge is the reactor design, how we can scale up the reactors, how we can increase the compactness of the reactor, how There are also an economic aspects of the reactors. The second challenge concerns mass transfer limitation, like aerodynamic, like the nature of the catalyst. We also do chemistry and chemical engineering by studying the influence of the competition, for example, effects, because the pollutant is usually present with another pollutant, so we can see what is the influence of the other pollutants. And the fourth challenge is the combination of the process with an idea, with the aim to increase the efficiency of the process. Of course, all these challenges are related. I mean that kinetics can concern also the combination of the process, and compactness concern also the combination of the process. I will give an example for each challenge. For example, the mass transfer limitation. Here we can see the principle of the photocatalysis. I will not develop this because my colleague and friend Lutfi will develop this after. We can see that the photocatalysis is a catalyst which is activated by UV lamp, and we generate some activated particles which will degrade the pollutants. So, for example, here we have a reactor we studied. This reactor is a tangential reactor, which we have the airflow entering from the right to the left. The catalyst is deposited on two plates, and we have between the two plates we have the lamp which activates the catalyst. So the airflow between the two plates. We note that the increase of the concentration lead to a reduction of the removal efficiency. It's normal because the increase of the concentration lead to more molecules to degrade. So as the active site of the catalyst are constant, so it's normal that the removal efficiency decreases. The most important thing to see is that the influence of the gap, it means the distance between the two plates. We see that, for example, for the concentration at 20, when the distance between the two plates are increased, we decrease the removal efficiency. This is the evidence of the mass transfer limitation. It means that the molecule has not the time to go from the bulk to the active site. You know, when we vary between 20 millimeter to 60 millimeter, we reduce the degradation from 60% to about 25%. We try to modelize this phenomena by taking into account the phenomena which occurs. We have a flow, a bulk of the process, and we have a boundary layer and the catalyst film. By writing the mass balance on each phase, in gas phase, in solid phase, and by estimating the value of the mass transfer coefficient by using classical empirical, semi-empirical correlation, we can have a model which predicts the removal efficiency due to the influence of the mass transfer limitation. Here we see that the removal rate variation by versus pollutant concentration. We see that the model represents correctly the influence of the mass transfer. You can see the same phenomena on water treatment. Here we have a falling film on the photocatalyst. We have developed a model taking into account the thickness of the liquid film, which falls on the catalyst, and then we see that you can have the influence of the removal of the pollutants. Another challenge concerns the reactor's configuration. It is, I think, our activity, our principal activity, which concerns to reduce the compactness of the reactor and to scale up the treatment and, of course, the efficiency. Here, for example, you can see that the classical configuration of the reactor is consisted on two catalysts. The catalyst deposited on the plate, and we have lamp to activate the catalyst. With a new configuration, which was developed by Brochy Technology, collaboration with Brochy Technology, we have the optic fibers that on that the catalyst is deposited. So the catalyst will be eliminated in situ by the fiber. This leads to a reduction of the size of the reactor. Here you can see the tissue. We don't need lamp for activate the catalyst. Only a LED, UV LED is necessary to activate the catalyst. When comparing the efficiency of the two configurations, we see that the new configuration is better. It's on orange. You have the removal efficiency is increased on the new configuration. This can be claimed that this is due that the catalyst is eliminated in situ, so we have more active sites generated. We see also that the selectivity, what we mean by selectivity is the CO2 formed by the degradation of the pollutants. In other words, it means when CO2 is high, it means that we have no other byproducts. We see that, we call this the mineralization. We see that the mineralization is better when we use this configuration. Also, we can see the energy aspect of the degradation. Here we represent the removal rate on milligram per hour per watt of energy consumed. We see that we have about 50% difference between the new configuration and the old configuration. It means that the new configuration is has more efficiency on energetical aspects. Some results are observed on water treatment. Here in classical configuration, we have a lamp on a tube where the water flows, and the catalyst is on the inner surface of the tube. By using photocatalyst of an optical fiber, we have a wire of the catalyst. Then we can eliminate it directly. So when we compare the two configurations, we have the same results. Another aspect we can, yes, I have not presented it. Here on blue, we have the removal efficiency, but on red, we have the surface area of the reactor. It means the compactness. If the surface area is great, it means the reactor can be compact. With same surface, we can have a reduced volume. This is an important thing, for example, when we have to treat internal air for the room or not. We have not many places to install a reactor, so when we reduce the volume, it will be more easy to install this. Another aspect of the compactness is of the reactor. It concerns the, the front flow. It means that the flow go directly to the catalyst. This representation or this configuration is interesting because it reduces the limitation due to the mass transfer, but they reduce the contact time of the molecule. There are two antagonist aspects. We also see here, for example, when we compare old configuration and new configuration, on blue, we have the old configuration where we use the lamp to eliminate the catalyst, and on orange and gray, we have the new configuration. Gray has more TO2 deposited than the orange, so we see that we have more efficiency also on new configuration, on violet, je sais pas comment on dit violet en anglais, we see the compactness of the reactor is increased. And another aspect is concerning the kinetics. What we say about concerning the kinetics is the competition effects between the molecules of the pollutants, between, for example, air and humidity, between on the water pollutant with organic matter, for example, and also for competition between bacteria and pollutants. For example, here we can see the influence of the humidity on the process efficiency at different inlet concentration on blue, red, and green. We see that there are two antagonist effects of the humidity. On the first time, we see that the increase of the humidity leads to an increase of the process efficiency. This is due to generation of OH point radicals, which leads to more degradation. And after a certain value of RH, we have a decrease of the efficiency. This is due to the competition effect between the water molecules and the pollutants, which reduce the efficiency. We developed a model based on Langmuir-Sherwood, which represents the variation of the kinetics, taking into account the constant of the reaction and the constant of the adsorption. We, on the right, we introduced the effect of the water vapor. W means water. We have a model that which will represent the variation of the kinetic under the influence of the humidity. We can see here the model and the experimental points, and we have the value of the different constants of the model. Another aspect concerns the competition between two molecules, for example here, between isovaleric acid and isovaleraldehyde. We can see, for example, that isovaleraldehyde, when it is alone black point and on mixture, is not influenced by the competition, but isovaleric acid is greatly influenced by the competition. When he is alone, we have about 10 milligrams degraded, but when he is in presence of isovaleride, he is reduced because this is due to that the isovaleride take the place of the isovaleric acid on the sites. Here also we developed on the same idea like the last slide, based on Langmuir-Sherwood model to represent the influence of the competition. Another aspect we can represent here, it concerns the influence of the bacteria, and are we, can we degrade the bacteria in the presence of the pollutants? For example, here we worked on by using Escherichia coli and chemical pollutants butadiol. We have developed a catalyst containing TO2 and a metal wire on silver or on copper. Here we can see first of all, the orange point represents the removal efficiency. We can see that the removal efficiency is not affected strongly by the presence of bacteria, but we note that the bacteria inactivation can be degraded when we have metal wires like silver or copper. But we note that the copper gives better degradation of the Escherichia coli. We have done another experiment with pathogen bacteria like Salmonella, like Listeria, like Cladosporium, but we don't do this in our lab. There are a lab which is abilited to work with this kind of bacteria. We see that the Salmonella and Listeria can be degraded by photocatalysis in the presence of the copper, but the Cladosporium seems to be resistant to the degradation. So the question is, maybe the plasma can play a role to reduce the influence of, to reduce the activity of Cladosporium. I represent this on the last. The last challenge concerns the combination of the process. The idea is to take into account the defect or the weak point of each process. Here you have the plasma. Just 2 words concerning the plasma. The plasma consists on a dielectric between 2 electrodes. We apply a high voltage, about 10,000 volts. Then we generate some radicals, free electrons, etc., which will degrade the pollutants. The TO2, well, everybody knows this, but Roxy will explain this. The principal weak point of the plasma is the bioproducts, which is the ozone, which is generated due to the presence of oxygen in the air. And the 2 weak points of the catalyst is the slow kinetic, essentially, for example, on water treatment. And the other problem by plasma, by photocatalysis, is the catalyst poisoning. When we have sulfur, for example, like H2S, but it leads rapidly to poisoning of the catalyst, so the process will not be efficient. So the combination of the 2 processes will lead to more interesting degradation and more efficiency. We see here, for example, that when we use the combination concerning H2S, we have increased the efficiency. For other pollutants, we also have a great degradation when you use the combined process. We can note that there was also, we have seen that there is a synergetic effects. It means that the combination of the 2 processes gives more efficiency than the sum of each process taken alone. I will explain this phenomenon later, but it's interesting that we have a synergetic effect. The synergetic effect is observed for many pollutants.
One last minute, please.
Yes, okay. So here we can see that the influence of synergetic effect on. But we also observed the synergetic effect for the other pollutants, for the competition between on binary system for for example. And the last one, for example, by microorganisms, we see that the use of plasma and photocatalysis leads to more degradation of the pathogen, even on Cladosporidium, which is reduced by plasma, and by increasing the energy and the resistance time, we can reduce greatly the activity of Cladosporidium. Well, we have the same. We can see the same thing on the water. We have the synergetic effect, and just towards synergetic effect is due to 4 phenomena. The first phenomenon is the enhancing of mass transfer due to ionic wind, which is ameliorate the mass transfer. Adsorption of active species, which increase the degradation by regeneration of plasma and ozone decomposition, which leads to more degradation. All these phenomena can occur same time. Well, to conclude, we have another perspective of our research concerned to understand more the phenomena of the plasma, the phenomena of the competition, association with activated carbon, for example, and so on, and improving mass transfer, for example, by generating turbulence and increasing the process intensification. Well, to terminate, I will show you that we have many activities on many collaboration now with very countries, Algeria, Morocco, Tunisia, and in Europe, etc. And I will thank here the last slide, our financial support like Partenariat Ibercurien, Institut Français, Prima, Union European, and so on. So, thank you very much.